Mercury is getting smaller, not quickly, not visibly, not in any way you would notice in a human lifetime or 1,000 human lifetimes. But right now, at this exact moment, the innermost planet in our solar system is contracting. Its surface is buckling. Cliffs are rising from flat ground where no cliffs existed before. The crust is folding inward, crumpling like the skin of a piece of fruit left too long in the heat. And there is nothing, not physics, not time, not any force in the universe, that will stop it. Mercury has been shrinking for 4 billion years. It will be shrinking when our sun expands into a red giant and swallows the inner planets whole. It will be shrinking, in whatever form it takes, until its core finally goes cold, a process that will take longer than the current age of the universe to complete. A planet, slowly, imploding, and we had no idea, until we sent a robot to crash into it. Mercury is easy to forget. It is the smallest planet, the closest to the sun, the one that hides in the sun's glare and is visible from Earth only in the minutes before sunrise or after sunset, and only if you know exactly where to look. For centuries, astronomers assumed it was boring. A dead rock, overcooked by proximity to the sun, geologically inert, scientifically uninteresting. The runt, the footnote, the planet nobody put on their mission priority list. They were wrong in the most spectacular way possible, because Mercury is not boring. Mercury is a crime scene, a world that survived the most violent event in the early solar system, that carries that violence in its very structure, and that is still, right now, feeling the consequences. Every strange thing about Mercury traces back to a single catastrophic moment billions of years ago, and understanding the shrinking means understanding that moment first. Pick up a cannonball. Now pick up a beach ball of the same size. The cannonball is heavier, obviously. Mercury is the cannonball, for its size roughly 4,880 kilometers in diameter. About 40% of Earth's mercury is absurdly, impossibly dense. It is the second densest planet in the solar system after Earth, despite being the smallest. If you could place Mercury and Mars side by side, Mars would be significantly larger, but Mercury would be heavier. The reason is what is inside. Scientists believe Mercury has an iron core that takes up approximately 85% of the planet's entire radius. On Earth, our iron core occupies about 55% of our radius. Mercury's core is not just large, it is almost everything. The rocky mantle and crust above it are a thin shell, barely holding the planet together. No planet forms this way naturally. In the standard model of planetary formation, rocky planets develop with roughly proportional cores, a balance of iron core, rocky mantle, and thin crust. Mercury should look like a smaller version of Earth or Venus on the inside. It does not. The leading explanation is a collision, and not a small one. Billions of years ago, early in the solar system's chaotic formation period, a protoplanet approximately the size of Earth struck Mercury. The impact was not head-on. It was a grazing blow, an oblique strike that tore into Mercury's upper layers and blasted them away. The outer shell, the silicate mantle, the crust, the lighter rocky material that should have surrounded the iron core was stripped off and expelled into space. Some of it may have been reaccreted by the sun. Some may have drifted into the asteroid belt. Some may have rained down on the other inner planets. What remained was the iron core, mostly intact, now exposed beneath a thin veneer of rock that barely constitutes a crust. Mercury is not a planet in the traditional sense. It is the naked core of a world that was killed before it could finish forming. It is the iron seed of something that might have been Earth-like, scraped clean by a catastrophe so violent that the evidence is written in Mercury's own impossible density 4 billion years later. A murdered planet, reduced to its skeleton. And that skeleton has been cooling ever since. Here is the physics of Mercury's slow collapse, and it is simple enough to hold in one image. Think of a grape. A fresh grape is plump, taut, full. Its skin fits its contents perfectly. Leave it in the sun. Watch what happens. The water inside evaporates. The flesh contracts. The skin, which cannot contract at the same rate, begins to wrinkle, to fold, to buckle inward on itself. The grape becomes a raisin. Mercury is doing the same thing. But instead of water evaporating, it is heat. Mercury's iron core formed at enormous temperatures, thousands of degrees during the planet's violent birth. Since then, it has been slowly, continuously radiating that heat into space. The core is cooling, and as iron cools, it contracts. It pulls inward. It takes up less space. But the rocky crust above it cannot simply float down to fill the gap. It is rigid, solid. It cannot compress the way the core compresses. So instead, it buckles. As the core contracts, it pulls the crust inward from below. The crust, unable to compress smoothly, folds like a tablecloth being pulled from one end. The folds push upward, creating massive ridges and cliffs that geologists call lobate scarps or thrust faults. These are not small features. The largest of Mercury's thrust faults, Discovery Rupes, stretches for approximately 650 kilometers across the planet's surface. It stands up to 3 kilometers high in places. It is a scar visible from orbit, a wall of rock pushed upward by the slow, relentless contraction of the world beneath it. And it is not alone. The Messenger spacecraft, which orbited Mercury from 2011 to 2015, mapped over 4,000 individual thrust faults across the planet's surface. Some are young, geologically recent, their edges sharp and unweathered. Some are old, their faces softened by billions of years of micrometeorite impacts. But here is what the Messenger data revealed that genuinely shocked the scientific community. Mercury has shrunk by approximately 7 kilometers in diameter since it formed. 7 kilometers. A planet has compressed itself by 7 kilometers. The circumference of Mercury, currently about 15,300 kilometers, is 7 kilometers smaller than it was when the planet formed. And based on the current rate of cooling and the heat still remaining in the core, it will continue to shrink. The process is not over. It is not even close to over. Here is where it gets genuinely unsettling. For decades, Mercury was classified as a geologically dead world, a planet that had cooled long ago, whose geological processes had ceased, whose surface was a static fossil record of ancient bombardment. The Messenger data changed this. When scientists analyzed the thousands of thrust faults mapped by Messenger, they found something that should not be there on a dead world. Some of the faults cut across impact craters, meaning the faults formed after the craters. Some of the craters are young, by planetary standards. This means the faulting that cut across them is younger still. And in 2019, a team of researchers reanalyzed seismic data and surface images, and published a paper suggesting that some of Mercury's thrust faults show signs of very recent activity that may be occurring in geological time, right? Now, not millions of years ago, not billions of years ago, geologically recent. Perhaps within the last tens of millions of years, a blink in planetary science terms, Mercury may be having earthquakes, Mercury quakes. The slow contraction of the core, the same contraction that has been building thrust faults for 4 billion years, is still happening. The crust is still being stressed. The faults are still moving. And if they are moving, they are generating seismic events. We have never placed a seismometer on Mercury. We do not know how often these events occur. We do not know how large they are. We do not know whether Mercury is cracking quietly, in slow tremors, or whether it periodically releases larger events that would register significantly on any scale we could measure. We sent 2 spacecraft to Mercury. Neither carried a seismometer. We listened to Mars for years with InSight's seismometer, and learned more about Mars's interior in 4 years than in all the decades before. We have done nothing equivalent for Mercury, a tectonically active planet, 77 million kilometers from Earth at its closest approach, and we have never listened to it. But here is the detail that should genuinely stop you for a moment. Mercury's core, despite 4 billion years of cooling, is not fully solid. Earth has a solid inner core and a liquid outer core. It is the movement of that liquid outer core that generates our magnetic field. Mercury has a magnetic field too weak, only about 1% of Earth's strength, but measurable and real. A magnetic field requires a moving conductor. A solid iron core cannot generate one, which means some portion of Mercury's iron core is still liquid. After 4 billion years of cooling, after shrinking the planet by 7 kilometers, after generating thousands of thrust faults across the surface, the core of Mercury has not fully solidified. This surprised everyone. A planet this small should have cooled faster. A planet this close to the sun, this ancient, with a core this large relative to its size, should have frozen solid long ago. The physics suggested a dead, solidified interior. The magnetic field said otherwise. One leading explanation involves sulfur. If Mercury's iron core contains a significant amount of sulfur, a possibility, given Mercury's formation environment close to the sun, the sulfur would lower the freezing point of the iron mixture, keeping a liquid layer intact at lower temperatures than pure iron would allow. Another possibility is that the thin mantle above the core, stripped away by that ancient collision, provides less insulation than a normal planet's mantle would, creating a specific thermal environment that maintains a liquid layer longer than models predicted. We do not know for certain. What we know is that inside a planet that is slowly crushing itself to death, inside a world that has been contracting for 4 billion years and will continue contracting indefinitely, there is still a churning liquid iron heart, still moving, still generating a magnetic field, still alive in the most minimal sense of the word. A planet collapsing around a core that refuses to freeze. In October 2018, the European Space Agency and JAXA, the Japanese Space Agency, launched a spacecraft called Bepi-Colombo. It is the most sophisticated Mercury mission ever built, actually 2 orbiters in one, designed to study Mercury's surface, interior, magnetic field, and exosphere simultaneously, answering questions that Messenger's single orbiter could not. Bepi-Colombo reached Mercury's vicinity in 2021 and has been conducting gravity assist flybys since. It is scheduled to enter Mercury's orbit in 2025. When it does, it will carry instruments that Messenger did not. Magnetometers more sensitive than anything previously sent to Mercury. Spectrometers capable of measuring surface composition at a resolution Messenger could not achieve. Instruments designed specifically to map the gravity field of Mercury with enough precision to infer the shape and density of the liquid core beneath the surface. For the first time, we may be able to directly measure how much of Mercury's core is still liquid, and from that, calculate how long the planet has left before the core freezes completely and the magnetic field goes dark. It will also, potentially, give us the best data yet on the thrust faults, their precise geometry, their depth, their age, and if there are Mercury quakes happening, Bepi-Colombo's instruments may be able to detect the subtle surface deformations they leave behind. We are about to learn more about Mercury in the next decade than we learned in all the decades before. Step back. Think about what Mercury is, stripped of everything but the facts. It is the surviving iron core of a planet that was murdered by a collision billions of years ago. It orbits the sun so fast that its year is shorter than its day. Its surface alternates between temperatures that melt lead and temperatures that freeze oxygen. It has polar craters filled with ancient ice that has not seen sunlight since the solar system formed, and it is shrinking, quietly. Millimeter by millimeter, year by year, the core cools and contracts and the crust folds inward, and new cliffs rise from flat ground, and old cliffs grow imperceptibly taller. 7 kilometers in 4 billion years. That is not much. That is less than the height of Mount Everest measured twice. But the process that produced those 7 kilometers is still running. The heat in the core has not yet dissipated. The contraction has not yet stopped. The faults are still moving. In the deep future, long after Earth and Venus have been swallowed by the expanding sun, Long after Mars has been stripped of what thin atmosphere it has left, Mercury will still be there, orbiting the cooling white dwarf our Sun becomes. Still shrinking, still generating its tiny magnetic field from a liquid core that refuses, against all odds, to freeze. It has been doing this for longer than complex life has existed on Earth. The thrust faults rising on its surface are older than the first fish, older than the first land plant, older than the first tree. Mercury does not need our observation to continue. It does not need our missions, our orbiters, our instruments. It has been shrinking in complete indifference to our existence since before our existence was imaginable. But we would do well to keep watching, because a planet slowly crushing itself to death around a core that will not freeze, inside a solar system that formed from violence and has never truly stopped being violent, is not a story about Mercury. It is a story about what everything becomes, given enough time, smaller, colder, quieter, until the heat runs out.